Okay, good afternoon. So it's my great pleasure to welcome you to this conference and to say a few words on behalf of the EPFL direction. I'm Ambrogio Fasoli. I'm the Provost and Vice President for Academic Affairs. These are the days of sustainability, of course, and today in this particular session we will discuss science for sustainability. That means a combination of elements that lead us to a balance between environmental, economical, and human needs. Of course, one of the key elements in this is energy. And this is represented in a couple of ways in this figure that I really like, especially the one on the right. But first, on the left, it indicates that energy amounts to 73% of the greenhouse gas emission. And this is something we have to keep in mind when we speak of sustainability and therefore also of CO2 emission. The graph on the right, the image on the right, is something that I also like very much. I often introduce it in my classes. It's a visual representation of the north and the south of the world to some extent, because the size of the countries in this world mapper graph or figure is made proportional to the use of energy per capita. And you can see really that some countries almost disappear in the map of the world, which is a reminder of how unfair it is, the distribution at the moment. And I think it's also reminding us that what we do about sustainability and about energy in particular, we don't do for the sake of our own small country or even larger countries in the Western world, but we do for the whole planet. And this is something we have in mind at EPFL in general when we attack the issue of energy. And I can say very immodestly for all of us that EPFL is really at the very top in the rankings when it comes to energy research and, of course, as a consequence, also sustainability research. And it's a broadband effort that we have. Here are just images that represent the different elements of our R&D efforts. About 100 labs. About 100 labs are actually dedicated to energy at EPFL. And I should say EPFL campuses plural, because of course these labs are across different locations. So we have wind, we have of course solar, we have carbon capture, utilization and sequestration, we have nuclear fission, we have nuclear fusion, we have materials for energy, we have socioeconomic studies, we have of course storage, batteries, efficiency, smart grids, transportation, and so on. So this is something that is really important to underline, not only because of our own spectrum of R&D, but also because it tells us something in principle we should all know, that there will not be a single silver bullet to solve the energy issue in general for the planet, and in particular even for Switzerland, and therefore when we do R&D in energy, we should keep this open mind to all the possibilities, all the options. One initiative that we launched a few years ago underlines this once more, and it also it was an experiment to some extent for our campus to see if there was an appetite for mission-driven research. And so we set up this scheme, which we call Solutions for Sustainability, so that groups could be formed, could be federated together to address issues about sustainability, of course, about energy and sustainability more in general, groups that otherwise wouldn't be formed. And also, the focus was, and still is, some of the projects are still going, on using the campuses, plural, as demonstrators for these ideas and for these technologies that are being developed. So we had two, and we still have two long-term and larger projects, led by Mario Paolone and Kumar Agrawal, and 5 shorter-term projects which have ended a few months ago, although there may be some small continuations for some of them. I can say, from my perspective, it was a great success because, again, coalitions and collaboration were formed that maybe wouldn't have been formed otherwise, and the results we have seen so far, and that we will see today, so I can let you judge from your own eyes, demonstrate and prove that really we are advancing along these lines. So I really look forward to the presentation from Mario, Kumar, and Josie later on today. These are the 3 that have been are representing this effort. We have initiatives on energy that also go beyond this use of the campus as demonstrator. We have a lot of initiatives in Valais. I'll say a few words about. We have also across Switzerland this clean energy, green energy and storage coalition that involves not only the academic partners, but also quite a few and more, hopefully, industrial partners. We also are in tight collaboration with the international entities, including IAEA, which is, of course, the one that deals with nuclear, both fission and fusion. As I said, energy is a big part. It's not the only part, of course, in sustainability, but we are aware of that, and so we have quite a few other challenges that are addressed at EPFL on the Earth ecosystems in general, water and land. We have several labs, 14 labs that do different things from fresh water, soil, microbes. We also look forward to presentations on this later on today. Marine and coastals, grassland, agriculture, fresh water, and so on. We have 7 labs that deal with atmosphere and climate. And of course, labs actually overlap in different areas, so activities are not in silos, but they are interleaved with each other. And we have also quite a big effort with 18 labs on construction and urban development. So I think we cover quite a nice and broad spectrum of activities, and we take advantage, we should do even more and more, we take advantage of the synergies and the possible collaboration among them. So, as I said, Valais is an interesting focal point for all of this. As you know, we have one of our campuses in Sion, where there are several chairs, several groups that are being deployed on a number of areas, specifically around sustainability and energy and storage. Also on snow and extreme environments, in collaboration with the Swiss Polar Institute, microbiome, ecosystem and water, as I mentioned, and also environmental applications of artificial intelligence. All of this, again, in a constellation of Sion, where there is a very nice critical mass now, and that's, of course, leading to more and more successes in collaboration with Lausanne and even other campuses around. Thank you very much for your attention, and I look forward together with you with the next conference. Dimitris will explain a little bit how we will work.
Thank you very much, Ambrogio. Just a very brief introduction of what is going to follow. So we have 3 sessions on different themes. In each session, there will be 2 presenters. At the end of each presentations, there will be a roundtable discussion, so please don't hesitate to ask questions at the end. Without any much of other introduction, first session is on energy transition. I would like to invite Professor Mario Paolone to start with this session. Thank you.
Thank you, Dimitris, for the introduction. So it's my pleasure to introduce you to the HeatingBits project. It's one of the 2 large initiatives that have been supported by the EPFL direction, as Ambrogio introduced in the Solution for Sustainabilities. And the project is particularly focusing on compressing the carbon footprint of data centers. So the motivation of this project is relatively obvious. If you look at the electricity consumption from data centers in 22-24 was about 500 terawatt hours. That were about 2% of the worldwide electricity consumption. This year, 2026, projections are to basically double these numbers, so reach 1,000 terawatt hours. If you look at the trend that the International Energy Agency is forecasting, it's more than exponential, of course, due to the need of artificial intelligence and associated applications. Now, what is the impact of this growth? Well, there are 3 major elements. So the first one is obvious, the inefficient use of energy. Basically, a data center produces heat, converts electricity into heat. The second point is the impact on the power grid, and that's a more subtle problem because we are incrementing the load of the power system, leading to congestions into the system and to the increase of an uncertain demand, or let's say a demand that is not entirely controllable. And this triggers other challenges associated to the amount of reserve that you need to compensate for the fluctuation of this demand. And the third one is, of course, the carbon footprint associated to the usage of this electricity. So what are the goals of the HeatingBits project? Well, basically three. So the first one is to develop a set of technologies and methodologies to basically do two things: reduce the carbon footprint of data centers and enable their scheduling. So the possibility of controlling the data center with a very high level of reliability. This is again to help the power grid to keep up with this increased demand. The second point is to validate the various technologies and methodologies into a first-of-its-kind demonstrator that we are building on campus in the CCT building, Centrale de Chauffe. We have a 50-kilowatt demonstrator that is under construction. And the third point is to involve data center stakeholders for tech transfer. We have created a board of industry stakeholders, which is pretty large. We are very proud of it, that are interested to absorb these technologies and eventually transform them into adopt them into the real world. So that's the scheme of the system. So it's relatively simple. So you have the data center here. It receives power from the power grid. Not only, it can also be powered by local photovoltaics and the local battery energy storage systems. It produces heat. So the heat can be either be injected into the heating district of the EPFL, or, that's a pretty interesting aspect, can be diverted into an organic ranking cycle, which is a low temperature ranking cycle with organic fluids that can reproduce back and inject back into the grid electricity. This element is particularly useful because it's increasing the exergetic efficiency of the whole process. I will give you some details about that, although time is not allowing me to go very deep into the details. So let's start from the servers and the need of harvesting the heat at the highest possible temperature. So to do that, we are using a direct liquid cooling. So DLC is a technology that existed since a while, and it can be conjugated in two different versions. Either you an on-chip cooling or an in-chip cooling. The in-chip cooling requires the silicon to be designed for hosting microfluidic channels. Instead, what we do is to basically do an on-chip cooling. We retrofit existing chip CPUs. That's an activity carried out by Professor Mattioli of the Power Lab. And what we do is, first of all, is to characterize the heating map of the CPUs by running typical workloads on the servers. In this case, we're using RCP workloads of our data center. And through an optimization process, we're capable of designing the microfluidic channels to maximize the extraction of heat. And here you see a realized cold plate that will be applied on the chip. The result is basically to reduce the thermal resistance. Here you see the thermal resistance over the flow rate of the cooling from commercial solutions to what we do by almost half. And the consequence of that is that we are getting access to a fluid that has a temperature that is exploitable, especially by the organic ranking cycle. Just to give you some numbers, we're talking about 75 degrees. So that's an example of the CPU cold plate assembly, and that's a realization. These are the various subcomponents of the cold plate, and this is the installation on the server blade. So we are now retrofitting several tens of these server blades for this 50-kilowatt demonstrator. Second point is this famous organic ranking cycle. So I don't know how much you're familiar with thermodynamics, but basically into a ranking cycle, we are using the phase change of typically water. So this is the typical diagram of in temperature entropy coordinates of water. And the problem is that to exploit in a ranking cycle a relatively high evaporation temperature, you need several hundreds of degrees that we cannot reach in a data center. So what an ORC does is basically to use organic fluids that are lowering basically the evaporation temperature and making it compatible with the temperatures of our CPUs. So this is the design of the organic ranking cycle done by Professor Hugues, that is a partner of the project. You see we evaporate around 70 degrees, and we condense the fluid at about 20 degrees, which is environmental temperature. So this is not sufficient. The other aspect that Professor Schiffman is dealing with is to optimize the turbine that is located here. Where is it? Yeah, it's here. that relies basically the expansion of your fluid in order to optimize its efficiency. So that's a relatively complex CFD simulation that is carrying out. But to optimize the CFD model, that's relatively complicated. What it does, his specialty, is to derive a result order model where it has less parameters to optimize, and this is specifically what he tries to do. And the nozzle that you see here and the rotor is the final product of his optimization process. So that's the machine where this device is tested. In terms of numbers, we are achieving 100% of heat from CPUs. 86% goes into the heating network of the EPFL, and 10% converted back into electricity. That's the efficiency of our organic ranking cycle. Yeah, it's not high, but in terms of impact on exergetic efficiency, this number is way higher than 10%. If you want, we can discuss the details later. Another key point, again, on the servers is the capability of forecasting their workloads. And that's an activity carried out by Professor David Atienza. So here you see the power consumption of the RCP, one of the blades of one of the clusters of the RCP over time. Here there are 3 days. And you have 3 curves here, basically 2 curves and 1 interval. The yellow one is the predicted one, the blue one is the actual realization, and this gray area is the 1090 percentile. So this is a forecast that is fundamental for the operational aspect of your data center. Why? Because knowing what kind of workload are executed is fundamental for the day-ahead scheduling of your data center, and also for the displacement of this workload, leveraging flexibility of the data center. So this is done through transformers, and here is an example of performance of these kind of forecasting tools, leveraging machine learning approaches. The fourth aspect is related to the power electronics and the power distribution. This is an activity carried out by Professor Dujic. Well, the distribution of electricity is all DC. Why? Because the server blades are supplied in DC, battery that is connected here is DC, photovoltaic is DC, and also the organic ranking cycle is connected in DC simply because this machine is spinning at 50,000 RPM. You cannot connect to the AC grid because you don't have frequency matching. So that's why Professor Dujic develops this concept of a solid-state transformer, where you don't have a standard transformer, but a matrix of switches, silicon carbide switches that are withstanding high voltage. Actually, we transform the medium voltage, typically 20 kilovolts, to plus minus 380 volts. We distribute power, and we also design high-efficiency server process supply. Just to give a number, the energy conversion efficiency of these devices is close to 98%, which is well above the industry standard available nowadays. The last part is what concerns my laboratory, which is the monitoring and the control of the whole system. And we carry basically 3 activities. I'm sorry for the very rich slide. So the first one is the long-term planning. Essentially, we formulate optimization problems to quantify which is the best mix of batteries and local production from photovoltaics to achieve the control of the data center and reduce its carbon footprint. I will not present this because I have no time. And then these other 2 layers are day-ahead and intraday control. So essentially, we quantify in a day-ahead bidding strategy what is the optimal schedule of the data center that it has to offer to the market. I look at Matthias because this is their business in hydropower plant exploitation. And then the objective is to minimize the operational expenditures, the carbon footprint, and of course try to stick to what you promise to the market to do. And then it comes the real-time control, where essentially new uncertainties are kicking in, and you need to stick to what you have promised in the ahead. That's an example of scheduling. So that's the RCP data center of the EPFL, 200 kilowatt of PVs, a battery of 200 kilowatt and kilowatt hours, and an ORC of 10 kilowatt. So on the top figure, you have the forecast versus the realization of carbon intensity. That's a specific day in July last year. So here you see the power profiles of 2 bidding strategies. So the black one is the power exchanged with the power grid, whereas the rose curve is the power absorbed by the data center with two types of carbon prices. That's a low carbon prices, what you're basically paying today, and that's what you should pay if you take into account carbon removal. So typically it's 265 euros per ton or 2,000 euros per ton. And here you see the possibility of scheduling the data center and keep supplying the workload execution. So here on the bottom, you see the carbon emissions. So on the horizontal axis, you have the total emissions, and on the y-axis, the probability. This is the PDF, so the density function with the high carbon cost, and that's with the low carbon cost, with an expected compression of almost 30%. So this is to showcase that we can control successfully our data center to achieve eventually our mission of carbon footprint compression. So with this, I finished, and thank you for your attention.
Thank you very much. So I may invite Professor Chris Moser to come and present something that complements well, I think, this presentation. Thank you.
You have to switch presentation, I guess, or? Yes. Thank you. So welcome to my talk. This is a talk about electricity self-reliance at EPFL, or towards electricity self-reliance. And my teammates here are PIs with complementary skills, in particular Mario in energy, Rizlan Bernier-Latmani in economics. You'll see how this plays into and machine learning and hydrogen with Professor Psaltis. So what happens if we fill roofs and facades with PV at EPFL? And this analysis was done by Sergi Agrawal from Fribourg campus. What you see here in this slide is that you can generate about 35 gigawatt hour total if you consider the roofs and the facades. So this number may tell you nothing, but it's a big number. So this number is comparable, or even higher, than the largest solar installation in Switzerland. You know, Cedron solar in the Grison is 29 gigawatt hour, and I told you if we put PV at EPFL, we are at 35. So it's a huge energy generation that we can have on campus. So how much do this 35 compares to what we consume at EPFL? This is a graph. It's not 2022, but 2026, actually. You see the amount of electricity that we consume at EPFL per year. It's 68 gigawatt hour. 35, it's half of it, more than half of it. So you see it's significant. So the story of this sustainability project was to see how to integrate that PV generation of energy inside the EPFL grid. And what we discovered, and that we'll go throughout here, is that if we go on the market EPFL, we can save quite a bit of money, but we have to be smart about it. And we have to do forecasting, economics, modeling, and storage. And this is the story that I'll tell you right now. So this is a graph that shows in black the price of electricity day ahead. So if you're on the market, this black curve on the left, you see the price of electricity over a 3-year period. And you see it oscillates. So first it fluctuates. Second, it oscillates between around 10 to 30. Right? On average, it's about 10 cents over 3 years. EPFL has about a fixed contract, right, to not take any risk, between 30 and 40 cents. So we're much higher. So why not going in the market? So there's a catch to it, and the catch is these other colors there. The blue colors and the green colors. The price is on the right. It's completely a different scale. It's 40 times higher. And I'll tell you, these prices are called the imbalance price. And the catch is these prices here. I'll tell you in a moment what they mean. So this is, okay, this is 3 years, so it's 23 to 25. This is the average price. If you look at another period, this was just after the war in Ukraine. You see this is the same scale for the price of electricity. It's really varying quite a bit. Here we're over 40, sometimes 60 cents per kilowatt hour. So the geopolitical period here was such that the prices were very high. So hence the self-reliance is quite important to avoid these geopolitical instabilities. So what is about this imbalance price? What's the catch? So the catch is this. So this is one day, so from midnight to the next midnight. So what EPFL has to do if we want to go on the market is to specify what is called a dispatch plan. So that black curve here shows what EPFL will consume the next day, and we have to estimate this the day before, at 11 a.m. in particular. So you estimate that black curve, you submit this to SwissGrid, and then the gray part is the, let's say, the uncertainty that you supply. So you have a risk in supplying this. So then the day arrives, and this is your dispatch. But actually what happens during that day, it's a little different. So sometimes you consume a bit more, sometimes a bit less. And the difference here in what you forecast to what actually happens is where the imbalance price comes in. So these big numbers in blue and green comes exactly here to bite you. So if you're wrong on your forecast, you pay the price for it. So this you have to avoid. And hence the game of minimizing that price imbalance here. So this is the name of the game. This is just to tell you, like during one day, right? During one day, this is a zoom. You see the fluctuation below. So the price fluctuates, the imbalance price fluctuates. So what this S4S project forecasted, we did an economic model to forecast these imbalance prices. So this is very important to forecast this because this is really what penalizes you. So we made a model and we forecast this imbalance price. So then what's the game? The game is to forecast both the PV generation, so the sun irradiance, and manage electricity storage via batteries. So batteries, lithium-ion batteries, and hydrogen, as I will explain. So how about PV generation? How do you know how much power you generate, right? So one of the project here was to look at, we took a different approach. We are at EPFL, we're very close to the mountains, the weather is uncertain, it's notoriously difficult to predict in irradiance in this area here. So our idea was to put cameras to look at the campus, and from the cameras looking at the clouds, decipher what the irradiance will be in 15, 30, 2 hours, okay? So we actually did that. So we have a camera, which is just behind me on the esplanade. We look at these pictures. We acquired 2 years worth of data. And then we trained a transformer model, which is a neural network, where we put the image for 2 years. We put data, weather data, and there's one output of this network, which is the irradiance, how much sun will be in 15 minutes, 30 minutes, 2 hours. We trained this, and then we compared with satellite data how we fared. And here, EPFL did very well. So the NeuroCam is what we call this is the EPFL model with the cameras, and you see this is the distribution of errors, right, over 1 year. And the bottom here is the error in kilowatt hour or megawatts, thousands of megawatts. So we are more picky here to the center compared to Solcast, which is a satellite imagery company which delivers forecast. So we're much better. We're much better than them because we're local. We look at local clouds with cameras. We can't figure out what it is the next day, obviously, because we have only a visibility of a few tens of kilometers. We can't see the next day, but we can say intraday. So what is not the problem? The problem is if you have more and more PV on campus, you see the level of uncertainty here. The blue curve here is the electrical load. So the electrical load is fairly known. There's about 10% variation. However, if you have PV, you still have the next day a large variation here. This is 3.5 gigawatt hour, which is the current capacity of campus, which is 10% of what it could be. And you see already the uncertainty here. And if you increase to 8 gigawatt hour, which EPFL will go into at some point, you see the effect. So it's super important to know the forecast of electricity from PV. So we did a model of the campus over 1 year, and we took the 35 gigawatt hour, so we assumed the full coverage at EPFL. We have battery storage, 30 megawatt hour, and we took the historical prices on the market, and we basically minimized this function here. The function is just the difference between what you forecast, what happens. You multiply by the price imbalance, and then the sum, you have to minimize this. So this is the game of the minimization algorithm. And how do we, and then the result of this then it's boiled down to a table like this one. And you see, if you put batteries, whether you use our method or the forecast from the satellites, the total amount of electricity cost here is of the order of 6.3 million. And if you have a fixed cost of the order of 30 or 40 cents, you're much, much higher, right? So it really makes sense here. It makes sense to go on the market and go with batteries. So the batteries that I've shown, there's a slide missing, okay. The batteries that I've shown, they've gone down tremendously in price over the years. This is the price of lithium-ion batteries. This was actually from the Telejournal last week. You see the batteries now go down in 2025. It's almost asymptotic. It's a couple of $100 per watt hour. This is not only at EPFL that it may happen, but it's everywhere in Switzerland. You see, this is the batteries installed or in construction in Switzerland here, and you see the amount of megawatts here for this system. So how big is a battery? We need about 35 megawatt hour. This is the surface area that you need for 18 megawatt hour. You see there's a bit of empty place here, but we can easily fit that into a 40 by 40 meters. And that would be about the space here on the bottom. 1 minute, I'm getting there. So you see the space here that's required for batteries. It's still very much doable to have this type of storage here on campus. And we need to go from 6 gigawatt hour to 35 to cover everything, to be less reliant at EPFL. So what I will leave you today is the different acronyms for EPFL. I look at the presidents here, and the new acronym is this. EPFL is the electricity powered fully local. Well, that's my last slide. I'd like to thank all the collaborators, also the students who did all the work for this project. Thank you.
Thank you very much, Chris. I would really like to invite now the speakers and the participants of the roundtable to stand up. Maybe you go and sit, please. And please, may we have the next slide, please, to present the roundtable. Oh, yes, thank you. Okay, and I will hand over the discussion to Max Chevron. So Max Chevron, he will be the moderator of the session. He comes from the Service Industriel de Lausanne. So Max, it's over to you.
Thank you very much. So Mario and Chris, you have been well introduced. Thank you for your presentations. And Matthias Gaumann here, I think most of you know him already, but just a quick introduction in case. He has been working for 10 years at EPFL with his last role as a Vice President of Operations, and has now shifted towards a new role in the hydropower industry, in taking the role as a CEO of Hydro. Hydro is a company that is involved into about 50 hydropower plants, into operating, maintaining, and securing the plants. So Matthias, now that you have this new role, I'm curious about all the innovations and challenges that hydropower is facing in this world where we are over and ever going into an electrifying world with all the consumption that is coming up.
Many thanks for this very kind introduction. And ladies and gentlemen, it's a pleasure to see you again. Pleasure to be back here. Indeed, working with Hydroexploitation currently. And so the question is about hydropower and innovation. And I would like to give a very short, I would say, story about this. So in 1880, one of the first, if not the first, hydroelectric power plant was actually built here in Lausanne, and that was to lighten the hospital, which today is known as the CHUV. And then a few years later, you had a coal supply issue during the First World War, where Switzerland was facing the shortage of coal coming from Germany. And there again, was an innovation coming very locally between Geneva and Lausanne, where one of the very first, if not the first, hydroelectric powered train was introduced between the two cities. And then the development helped to essentially industrialize Valais, where the aluminum industry and the chemical industry benefited from the hydroelectricity that was introduced at that time. And if you go back 50 or 75 years, that was about the time when our parents or grandparents built most of the dams in Switzerland. And that was also the period where the nuclear power plants arrived. And there is a very nice complementary between the two. If you think about just Grande Dixence, Grande Dixence is a hydroelectric power dam which is located in Valais. And it has an output power of close to 2 gigawatt, which is essentially the power of 2 nuclear plants in Switzerland. And that is very complementary to the nuclear energy, because you can essentially close the valves, shut down the plant, come back on the next day, which is something which you cannot do with a nuclear plant. So where do we stand today? We continue with innovating in the hydroelectricity sector, and the new trend is in a pumped storage hydroelectricity plants, which means we take benefit of essentially 2 lakes, one which is at a higher altitude and the other which is at a lower altitude. And whenever there is energy demand, you flow water from the top to the bottom and you produce electricity. And when there is excess energy on the market, you do the opposite, where you pump water from the bottom to the upper lake. Now, if you think about some of these infrastructures, they have powers, and I'm sure we'll come back to that afterwards, in the range of nuclear powers as well. So you can essentially switch on, switch off a nuclear power just essentially by manipulating the valves.
Thank you. On my side, working at SIL, we are one of the DSOs of Switzerland who are faced with all these imbalance costs, as Chris has also mentioned in the presentation. They are rising because of all the uncertainty coming up on the grid, where the cost is high because Swissgrid has to activate flexibility and needs to engage these reserves at a cost that are transferred back to the DSO and then transferred back to the end consumers. And we have a factor 5 of our cost that has increased in the past 5 years. How are each of your works in terms of flexibility in hydro, maybe in data centers as well, in forecasting, can actually really go from research and innovation to the market? And I'm curious about maybe all your inputs onto this challenge that we're facing in DSOs and the will to reduce the electricity bill for the end consumers, where for the moment the trend is really going in the wrong direction. So whoever wants to start, thank you.
Well, that's the quest for flexibility, right? We are trying to squeeze as much as possible the possibility of controlling loads, energy storage, and power generation, as Matthias was also mentioning, to adapt actually the power equilibrium to the stochastic boundary conditions that renewable power generation is imposing. Basically, we are chasing the production from renewables instead of chasing the loads. So historically, what power systems were doing was basically to adapt power plant output to track the load demand. Now what we're doing is completely do the opposite. So we track the production demand, the production from renewables, thanks to flexibilities. Regarding the specific aspects of data centers, we are about to publish a paper where we are quantifying the economical value of the flexibility of the data centers. And according to the market conditions we're experiencing at the moment, the most of the value is for energy dispatching. We see very little value in data centers to participate to the reserve market, because the impact that this has on the rescheduling of the workload clashes on the revenues that the workload execution time is required by data centers, basically by the customers of the data centers, that requires a certain certitude of the execution of the workloads. instead, moving large chunks of workloads together with usage of batteries will be probably the best flexibility option for the data centers and therefore participate to day ahead and perhaps intraday energy scheduling. So this is the added value that we see from our research of data centers' participation in flexibility markets. And they will play a huge role in the future considering the amount of capacity that we are installing at the moment.
Yeah, and the question of batteries or storage. So I looked at the Offen website, and in Switzerland, every installation of PV, half of the installation comes with batteries now. So 50% has batteries. So it's coming because of the prices going down. And as you saw on the graph that I've shown in Switzerland, there's a lot of projects, giga projects, going, to being developed with batteries. There's one in Germany, which is close to they're not lucky because they don't have that many dams over there. So they're building a 4.6 gigawatt hour battery close to Poland. Abu Dhabi has 30 gigawatt hour plants with batteries, so it's going everywhere. So I think it's the trend for lithium ion, but also near the border in Basel, there is flow batteries that are they are based on chemical. So it's not only lithium ion, right? There's hydrogen, there's flow batteries. So I think the storage is necessary, and I think the price is so low now that it's the time to actually, when we put PV at the EPFL, to put batteries and storage with it. It doesn't make sense to do it without it. It makes total economic sense today.
Does it come into competition with flexibility from hydro, or?
Well, it certainly does, but probably not exactly at the same scales. So if I take the example of one plant, which is Norderdrance, which has been commissioned in 2022, and there are actually two similar ones in Switzerland. Norderdrance has it's a pumped storage hydro power plant, has a power output of 900 megawatt, which is about a nuclear power plant. It has a storage capacity of 20 gigawatt, which means 400,000 electric car batteries. And it has the particularity that you can actually either produce or store energy by essentially reversing the pumps into turbines or turbines into pumps. Now you do this in 5 minutes with an efficiency which is close to 80%, and you don't even see the facility. To see the facility, you have to go into the mountains, 6 kilometers inside, 600 meters under the ground. And that's where you can actually turn on, turn off a power plant of the output of a nuclear power plant within 5 minutes with this efficiency. So it is for large-scale, I would say, adjustments and power on demand on the grid, and maybe less, I would say, local in that sense.
Thank you. And before turning to the public, maybe one question on how maybe business models or different aspects have changed since winter 22-23, where we had risks of energy shortage. The new plan has been set. There's a hydro reserve ordinance that has been set so that hydropower plants could monetize some reserves in winter. So I'm curious about the business models, how maybe it changed for the hydropower plants. And in terms of consumers, it's first the large consumers that have to cut their energy first if the Auster plan comes into action. Switzerland being a bit cut off from all the deals with Europe, hopefully coming back again. Does this prevent maybe data centers for considering setting base into Switzerland because they have some risks of being shut down, or is this not an issue for the moment?
Let's say that's a good question. At the moment, according to the information I have, there is not a decrease of demand of data center in Switzerland. Switzerland is one of the countries in Europe with the highest penetration of DCs. The first thing is Ireland, for obvious reasons, due to cooling. But then per capita, it comes Switzerland. We have about 80 large-scale data centers. And according to my information, there are several requests of hooking up data centers of the size of 0.5 gigawatt directly on the Swiss grid transmission system. And this demand is so pressing that by the end of the spring, Swiss grid will release a grid code specifically designed for data centers. So at the moment, we don't see such a decrease of demand. And in parallel, distribution systems operators, even in the region, like SEG, for instance, in Geneva, they are seeing requests of connection of data centers of medium, small size, in the range of 20 to 25 megawatts, and the numbers keep increasing at the moment. So there is not such a coupling between the EU agreement and the connection of data centers at the moment in Switzerland.
And maybe on the business models for hydro, does it have an impact, or?
Well, I think it leverages the business model of hydropower. So if we look at the global electricity supply in Switzerland, about 10% is solar, and that is, it will increasingly be predictable, but it is hardly predictable. Then about 30% is nuclear power. This is not agile at all. It has to operate, you cannot stop it. And then about 60% is hydropower, which is agile, so you can turn on, turn off. So now the business model for hydroelectricity is essentially you collect water, from rain and from melting snow, you store water, and you turbine the water to produce electricity on demand. So what the ordinance has introduced is essentially a minimum level that needs to be kept in the dams, such as to ensure that there is a reserve when needed, and that there is sufficient power on demand that can be delivered. So in a certain sense, the ordinance is actually leveraging the business models of hydropower.
Thank you. As time continues to go, maybe do we have some questions from the audience for the participants? Yes, please.
Okay, thanks. I have a question for Matthias. So as you know, climate change is upon us, and it's predicted that there will be less precipitation, less storage of water in the form of ice and snow. And so since much of the storage of water for hydroelectricity originates in this form, what's the prospects of this sector, and how is it going to also be taken into account the downstream biodiversity in the streams, which dependent on a certain minimum flux of water coming down?
Thank you for your questions. First, the dams have been built. The assumption of global warming wasn't there. So it was not a question of taking benefits of the melting of the glaciers. It was of the yearly cycles. There was one element you said that the precipitations were reducing. I think this challenged actually. I think the amount of rain or the amount of water that comes continue to be high, but it comes in water, not in snow. That's true. So the core element continues to be here. And then the benefit that we have today that actually water in snow is a way of storing water, which won't be the case tomorrow anymore if there is no glaciers left, means essentially that you need to increase the storage capacity, so number of dams or height of the dams, so to increase more than anything else. Now, some of I would say typically the pumped storage hydro dams, you actually are in closed cycle. So you have two lakes and you rotate within the lake. You're not much depending on, and actually over the year you consume energy because you have a loss of efficiency, but you have power on demand. Now, regarding the downstream effects, notably on the rivers and the ecosystem, there are very clear laws here which are in place. How much water needs to be kept into the rivers, such as to maintain the the life in the rivers.
Thank you. Maybe one last question. If not, I think we can.
Yeah, there is a question. Sorry.
I have a, maybe for you, Mario. Do we have enough data, and do we work enough on the environmental consequence of disposing of batteries? Because, of course, there's, I mean, the argument is, of course, very convincing. We need batteries together with PV's system and so on. But what about the longer term?
Yeah, that's a very good question. We just closed a Nino-Swiss flagship project called Circularity, where I was responsible of one of the sub-projects, where we were analyzing basically three aspects of the life cycle of batteries. The manufacturing of the batteries from recycled materials, recycled from materials, and was a task done by EMPA. The extension of batteries from first to second life, and this is what done by my laboratory. And the third activity that was about the dismantling of the second life battery to produce materials to be then reused in the first manufacturing process. There are several good news. So the first one is that we proved in my laboratory that nowadays technologies of batteries can guarantee an energy throughput, essentially a number of cycle in charging and discharging in the second life application, typical in grid applications, which is equivalent or even larger than the first life if into electrical vehicles. We also did a very big project with Stellantis that is going to implement a business model to buy back the batteries of their cars, so basically sell them to power utilities. And the guys at EMPA, in particular Corsin Battaglia, have demonstrated the possibility of building cathode materials with 99% of materials coming from recycled batteries. So this project was very much instrumental in addressing your question and demonstrating basically the possibility of creating a circular economy for battery materials.
Thank you, everyone. I think we can close the roundtable. Thank you for your participation.
Big applause for everyone. Thank you very much. Thank you very much, Max, for running the session as well. And I really enjoy very much the last comment where there is some hope for making things sustainable, not only ensuring the energy transition, but in a sustainable way. The next session will be about mitigating carbon, basically. So I would like to invite Josie, Hugues. It's about technology for climate neutrality. And it will be, as you can see, Josie, Hugues, and Kumar Agrawal will be presenting the results from the solutions for sustainability projects. Thank you.
Thank you. Thank you very much, Dimitris, for the introduction. So we're going to have a bit of a small change in direction, and I want to talk to you about food. And we're going to start in the field. So if we think of where our food comes, it has to be grown. We need resources. We need water. We need nutrients. We need physical space. All of this requires resources and energy to grow. And even when we grow it, a significant proportion of this is left in the field. It's either damaged, it's considered unsuitable for consumption. So we have huge losses already and huge resource usage just in the field. Then somehow we need to get it to the consumer. These growing infrastructure, these fields are not typically where we live. So we need some kind of transport system, again, resource usage to get it from the field to us in our shops or other ways we can purchase this. And while there's some huge advancements in making this more energy efficient, this is still, of course, takes resources, and also it takes time, which also reduces perhaps the nutritional benefits of this food and reduces shelf life, also leading to waste. So we get our food, we enjoy it, we have a nice meal. We then also have waste. A lot of plant waste comes from unused parts of the plant and just unconsumed food or other wasted food. This typically might go to landfill or other, where if it's let to rot naturally, this will then lead to the release of methane, which, as we all know, is not good in terms of greenhouse gas emissions. So if we look at our current food systems, not only is it hugely resource intensive, it's also very lossy, and we don't have any circularity. We're really not looking at how can we design food systems that are really optimized. We're trying to connect and create more of a circular approach so that we can reduce losses, improve efficiency, and also develop and develop more nutritious food, contributing also to public health and also enjoyment, because I think food is also such a part of our community and culture. So with this, and we can look, of course, specifically within Switzerland, what is the impact of food at this global, at this kind of country level in terms of greenhouse gas emissions, and looking as we go really from the infrastructure and through to the field to transport waste and the consumer, where these losses come. So there's huge opportunities here to rethink our food systems and how we can bring these closer to consumer, reduce losses, and also reduce waste or make better use of this waste. So we're very lucky to have the opportunity as part of the Solutions for Sustainability funding and opportunities to really look at on campus, could we try and close and optimize the food system in an urban environment? So really here, cutting out this transport, and can we look at making nutritious food whilst reducing these losses? So our approach was to combine waste processing with growing, but also using robotics, control and optimization to try and both reduce losses at the growing stage, connect the outputs from our growing stage. We get food, but we also have waste. We have roots, we have extra leaves, other parts of the plants that are not used for food. We take those to our bioreactor, where under anaerobic conditions, this is digested then into methane, so biogas, which can then be returned in terms of energy. But the other interesting thing is out of our biogas, we also get not only methane, but we also get essentially a fertilizer. So we can then use that coming back into our growing system to reduce our resource usage there in terms of nutrients in this way. But for this to work, we've got to really understand how do we grow efficiently, how do we understand also the connection between growing and our bioreactor to optimize through control approaches to try and develop a more efficient and sustainable solution. So really building upon how we can look at new processes such as this bioreactor to make use of both food and also the waste products we can get from that. So aeroponics are actually being widely explored. There's some very big facilities we already have in Switzerland. But one problem we really have with these is how to automate these in some ways such that we still don't get wastage. We have early detection of pests. There's some big challenges with if we get any pests within the greenhouses, these spread very widely. And we also get only singular crop growth at the moment, which is not optimal for our bioreactor. And also if we maybe have a local kind of urban environment, maybe we don't just want to grow lettuce because there may be other more nutritious or balanced crops that we can grow. So we've been looking at how we can bring robotics and control into the growing system to both reduce, again, the resource usage and also increase our output, both in terms of the food and also our waste. So we've developed this aeroponic growing system where we have a number of cable-driven robots that can operate alongside a number of growing units, as you see here. This allows us to grow a variety of leafy greens, also peppers, arugula, basil, and also most recently tomatoes as well. So with this modular growing system, which runs on cables, which can be placed around aeroponic systems, so this can be used in a very scalable way in greenhouses, in any growing system. We have modular end effectors that the robot can choose between for gripping, for harvesting, for cutting, also for harvesting, for imaging systems for monitoring, and inspection, and also some for leaf turning, which is also important for being able to see if we have pests under the leaves. But we need some control for this, and we need some way that this can happen in an automated way. And we really want to automate the full process of growing, right from seeding, so taking our little seed inserts and putting these into our aeroponic system, to monitoring and also to harvesting. So we can have this way an automated system where we're harvesting at the optimal time, looking for early pest detection, reducing waste in our system. And to do so in our system, we have our ARM systems which go alongside the growing infrastructure, and we use this teleoperation system. This allows us to control multiple arms at once, and we can, with human demonstration of certain tasks, be it harvesting, cutting, as you can see here on the right for the harvesting, or monitoring, we can teach or demonstrate control, which can then be generalized using either small learning models or more traditional control. So this allows us, with very small amount of human data, to train our robots to then perform these varied tasks on different crops. So now we have the ability to go from planting through to harvesting across different crop types. And although we see quite a lot of work in agricultural robotics, the ability to work across crops is really not seen so much. This gives us a more generalizable approach to automating crop generation. Now, we harvest when we have got to the point where we see the crop growth is no longer increasing. We harvest and we can now eat some of this plant, but we have this waste. And this is the waste that we really do not want just going to landfill or otherwise. We want to take this and really try and return as much possible value from these resources, both in the form of biogas and also in the form of nutrients. So starting from our plant waste, we perform some homogenization, pasteurization, and then we feed our digesters. Now, typically, for example, in Lausanne, we have many of these very large-scale bioreactors where we perform and process this biowaste on a very large scale. But for us, we've been doing this on a much smaller scale where we can actually control within each of these cylinders, which reflects one each of these big bioreactors we might see for large industrial scales. We can control certain parameters, be it the temperature, the mixing rate, and also the feed rate. So this allows us to try and now optimize the conditions for converting our waste into biogas and also nutrient-rich solid waste. So we take our plant waste and we vary our control parameters to try and both maximize the volume of gas and our gas composition and also our solid and liquid phase. Now, what we get out of our anaerobic digester is a little bit hard to process because this is a biological system, so it's very sensitive to changes in temperature control and mixing rate. So it becomes a little bit more of a challenging control problem to deal with. So, for example, here on this plot, we're showing what is the biogas generated from 4 different reactors when we start feeding. So we see this big feed, this big peak in biogas across a number of the reactors when we introduce our waste into these reactors. But then this settles down to our steady state conditions. But we want to look at how we can put minimal energy and resources into our bioreactor, but maximize our gas input. And what we can see is we can perturb these reactors at different points in time to stimulate this gas generation. So with this, we've been looking at, first of all, just how we can play around with operating points in terms of temperature, mixing rate, and others to maximize gas output while minimizing energy input. But also, can we then have closed-loop dynamic control of control parameters such as temperature or mixing to further optimize our gas production? And with this, we can really investigate different control strategies and how these affect our biogas production with respect to our input power and how we can really try and minimize our input while maximizing our output biogas in general. So we also need to connect this back to our crop growth because we're growing different crops. These lead to both different amounts of biogas generation, but also different nutrients. So looking at different crops, parsley, basil, arugula, we've really looked at how the diseases map to different nutrients and also building different models of the biogas for different control parameters for our different crops so we can optimize for different crop systems. So this now allows us to optimize our biogas reactor for different crops and also then look at how is this going to help from our bioreactor, our NPK, so our fertilizer in terms of growth and selectively choose which crops can help for the next cropping system. So in this way, we can try and connect our growing to our anaerobic digestion, making use of waste, connecting what we can from the bioreactor to the aeroponic growing system and vice versa. We can then look at how we can really benchmark and compare with in-field growth. And obviously, we have big challenges in terms of making use of natural resources into light, water, and how we can really improve the efficiency, and how we can really also consider the lifespan of this hardware and how to overcome the embodied CO2 and what scales this needs to work out to become efficient. But I think what's really exciting is how robotics and AI can really assist in creating new feed systems. And also look to not only looking at maybe sustainability in terms of resource use, but also wider sustainability in terms of health, and also for the role of food, also I think culture, and how this brings and plays a role in society. So with that, I'd just like to thank the Solutions for Sustainability Committee, and also Dimitri also for his support, and also Agroscope, and also the students who've worked in this project. Thank you.
Thank you very much, Josie. I think we have plenty of discussions about all this later on. I would just like to invite Kumar to follow up with his own presentation.
Thanks, Dimitri. I will first start with thanking the leadership team, especially Ambrogio. He had to leave for some other meeting. But this could not have been possible without the support, because the kind of the project we are doing is typically what is not seen at the university level, because we are going from a typical university level towards a typical pilot plant. All right? We are trying to bridge the gap, especially in CCUS, from what we can do at the university level to where we go to the next. So I focus on waste incineration plant in Switzerland, just like Europe, has this big problem of decarbonizing hard-to-abate sector, and waste incinerator is one of them, not just because of the energy that it provides, but also because of waste circularity. And now we also have half of these biogenic waste, half of the waste is biogenic. So it's very interesting if you think of 2050 net zero scenario. And through this S4S CCUS project, what we are doing is we are building a full value chain of CCUS at a waste incinerator plant in Valais. The name of the plant is NAV. And if you see in this cartoon on the right, what we are trying to do is building the first unique carbon capture plant, which will have a capacity of about 1 ton CO2 per day. Not only that, because carbon capture is commercial, we will do it with a capture cost at scale of about $30 per ton. And this is really what makes this project very interesting, of reducing the capture cost. Then we will capture the CO2, and we just had a very interesting discussion of energy storage. And one of the things that we are doing is building Power-to-X platform, where we will take renewable energy, make hydrogen, and convert that into methane with energy efficiencies above, CO2 to methane energy efficiency above 70% with 100 kilowatt demonstrator. And the third aspect of that is a large-scale aspect is geological CO2 sequestration, where we are improving our understanding of what happens to CO2 if we inject it at 800 meters depth over a time scale of year. And this could really help us in Switzerland, where we have a lot of debate on CO2 storage. So I'll start with the first technology. And so the capture technology, the reason we are so excited about this is because we have this new innovative technology based on porous graphene. Now, what is graphene? It's a single layer of graphite. It's a Nobel Prize winning material. And the EPFL technology is really to take graphene and incorporate tiny holes or pores in graphene, all right? And when we do that, we are able to remove CO2 from all the other components that we have in the flue gas. And because these holes are just 1 atom thin, we can have record high carbon capture performance, right? And this is really the crux of this technology. So what I'm now saying is the technology is no longer at a small, tiny scale that we see in the lab. We have scaled it up. It's now at A4 sheet size. With a lot of support from Valais and GasNat demo projects, we have now done an industrial campaign of flue gas separation, real flue gas separation. containing NOx, also containing SOx. These are the real contaminants that often lead to technology failures. So with those, we have shown that these membranes are quite stable. And now we are running a testing unit at EPFL, which shows that where we can test various compositions of the flue gas. All right, so with that, I would like to show you this slide, where a study that we have recently concluded. And this is really interesting because it shows that such kind of membranes could be very attractive, not just at the waste incinerator plant that I was discussing, but across the full emission sector of CO2. So on the left, what you see is a natural gas power plant, which has dilute CO2. But on the right, all the way, as you increase the CO2 concentration, all the way to cement plant, which is very strategic for Switzerland again. And one of the two things that come out of this is because graphene is so stable, it's an inorganic material in SOx and NOx, it will have a longer lifetime. And so this is also very interesting for sustainability, for which we are here today. And the second aspect is because the flux of graphene is so high for CO2, we don't no more need a large capture unit taking the shape of a huge building, but those units could be integrated into a small container next to the emitter. So this is very advantageous for operating such a plant. And with this solution for sustainability project, one of our unique goal was to sort of break this critical barrier in the scale up, where we say, okay, now we are at A4 sheet, how can we manufacture this technology into several hundreds of meters square area that we need for going to a large scale plant? And this is where most of the technology fail. Very happy to say that now we have developed a first of a kind, unique roll-to-roll manufacturing tool for such a membrane. This is in collaboration with Vivek, who is at STI, and where we are able to replicate each of these steps that we do in the lab on a continuous moving roll-to-roll tool. And this allows us to upscale the production of graphene membrane. I said 1 ton per day. That requires 40 meters square of graphene. With this tool, we can do that in just a couple of days. Of course, we have to validate this. This tool is arriving at EPFL now. We have a period of about 1 year to essentially make sure that we can calibrate, we can fix all the issues that are in this tool. All right, so where we are now, so we are in 2026. In the next year, we want to essentially finish the step, install the membrane skid at NAV, and implement 1 ton CO2 capture. After that, that captured CO2 will be stored as liquid CO2, which will go for the Power-to-X project. And talking of Power-to-X, this is our project where we are taking CO2 and converting that into renewable methane. And this is essentially based on this concept of heat integration between solid oxide electrolyzer and a methanator. And the idea is very simple. If you take solid oxide electrolyzer and give it steam, the conversion from steam to hydrogen happens with near 100% efficiency. Now, where does the steam come from? So if we now want to convert CO2 into methane, we need a methanator. Methanator is exothermic, so that produces steam, right? So if we integrate it, we can get more than 70% efficiency. And this has been something that Jan van Erle at STI has demonstrated. At 10 kilowatt scale is currently doing that at 30 kilowatt scale. And with this project, we are demonstrating that. We are going to demonstrate that at 100 kilowatt scale. So the good thing is we have acquired the 100 kilowatt solid oxide electrolyzer. It is currently sitting at GasNat for initial testing and validation. And then this will move to NAV plant next year for CO2 to methane project. All right, so this was the CO2 storage part I talked about, where essentially the key issue is the following. As the researchers in the lab, we are studying small samples at millimeter to centimeter scale, but in the field, we are going to really large areas, right? So we're talking of kilometer scales. But kilometer scale corresponds to millions of years. Lab sample correspond to days to months. We need to understand what is happening in between. All right, so here with Eleni and Lies, we are developing this unique geological sequestrator, which is at the meter scale, where we will be able to confirm the stress and the pressure that we see when we inject CO2 to 800-meter depth. And this will allow us to improve the models for predicting what happens to CO2 when we sequester it at that depth. So this is just a simulation showing this injection. Where we are now, we have now identified and validated the materials that will mimic a typical underground condition, a cap rock and the reservoir. And now we will start the injections, and that will be essentially be studied over a period of time to really improve the models. All right, so we also have a few other things going on at a smaller scale at Solution for Sustainability project. One of them is direct air capture. And we want to reduce the cost of direct air capture. You all probably know of Climeworks, which is sort of doing this at a large scale, but they have a high cost, a cost somewhere between $600 to $1,000 per ton. And the high cost is really because what you see in this pie chart here is because the material that they use is not very stable, and they have to replace this material every 3 to 6 months. And with this project, we are developing these CO2 sorbents, which will have much higher stability. So here is one of the data showing multiple cycles of adsorption and desorption of CO2 to show that we are actually there. And then the other aspect is, why can't we, or we could potentially combine processes together, right? So adsorbents are very good at a small concentration of CO2. Membranes are very good at higher concentration of CO2. So we have now completed this work, which is in the preprint. We show that now the cost of direct air capture can be cut down by half, down to $250 per ton, right? And this is using commercial material, not even the most stable material that I showed you in the previous slide. All right, so reaching towards the end of my talk, I want to emphasize that technology alone is not enough. We also need to work with the policymaker. Sasha has developed some divergent scenarios for Switzerland. Why divergent? Because we just don't know the future, right? And now we are working with policymakers because some of these divergent scenarios do lead to net zero 2050. We are working now with industrial collaborators to come and work with us with the Solution for Sustainability CCUS project. We are working at an industrial scale. We already have collaborators such as GasNet, NAV, Solidera, spin-offs like Divya, and so on. If you are talking to industry, and if you are also working at EPFL and wants to look at this, collaborate with us, would be really great. We'll look forward to that. All right, so on June 15, we have a very interesting event. It's a CCUS stakeholders dialogue, where we are calling academicians, policymakers, government, students. So I welcome you to join, especially if you're a student, or if you want to encourage the students to come and present a poster at this event. This is very welcome. We will have a student award, which will be sponsored by Nature Sustainability on the topic of CCUS. So just wanted to advertise that. And just before I conclude, I want to say this kind of project, again, thanks to the direction, Ambrogio, on creating this Solution for Sustainability project has inspired us to go even further, develop even improved technology that could feed into the pilot projects or the testing units that we will build in Solution for Sustainability. So this is our NCCR separations led by Wendy, and we are going to build more innovative technology that feeds into S4S. All right, so I'd like to thank the team which worked behind this.
Thank you very much, Kumar. Josie and Kumar, maybe I invite you to take a seat, and I would like to invite Julian Barth to monitor a roundtable discussion. Julian is a third-year bachelor student, and it's quite courageous that he wanted to do this moderation. Thank him very much. And actually, he's also not only a student, but he's also the president of the EPFL Carbon team. So, Julian, over to you.
Thank you very much. My name is Julian, and I'm a student here at EPFL. And as Dimitri said, I'm president of the Carbon team. So it's a MAKE project, which is working with Kumar and Wendy Quinn in Sion. And we're developing a direct air capture module here on campus. So as students, we're very interested in the impacts your technologies can have, and especially how they can contribute to a greener and more sustainable future. And as a warm-up question, I wanted to ask, which impacts do you envision for your technology in the best case scenario in 10 years' time, so by 2036?
Maybe I can sort of start with that. I think what will happen in 10 years, and we saw, this is probably also linked with the previous panel that we had, is currently we see CO2 as a waste, right? So, and with the use of CO2 as a feedstock, for example, from CO2 to methane, and we also have a project on CO2 to higher value-added chemicals such as ethylene, I think we will sort of change this market on the mindset that CO2 is no longer a waste. It's an important feedstock, right? And what will also happen with all of the work that is going on CO2 capture technologies and so on, and there are a lot of policy hurdles, there are a lot of economic hurdles. As we go along in the next 10 years, I expect to see these hurdles to be reduced in their challenges. And we will have a little bit more integration between renewables, storage, CO2 capture, CCUS projects, and things will all come together and fit very nicely.
And then on my side, I think we need to see a change in our food systems. And I think that has to start now, and I think we have no choice as well because of the changes in climate. And currently this is not happening fast enough. We have no choice, but we need to generate the food to feed everyone. And I think also looking beyond Switzerland, this is even more pressing in other countries. But we need to see a change in the way our food is grown, and this is not just perhaps through growing locally, but even in fields in general, how we can deploy robotics and AI to have multi-cropping, to move away from having just uniform growth of one type, to really close the gaps in any way, looking at how we're generating waste, how we can reuse this. And again, not looking at waste as just something that we do not worry about, but how can we actually extract this, use this as a resource, and kind of bring a new way of thinking about our food systems.
So both of you talked about changing our habits, and oftentimes policy seems like kind of a hurdle to scale up. Do you think that right now your technologies could actually be competitive on their own? I mean, with the current policies we have and current market competitions?
Yeah, this is a great question. I mean, currently the policies, there is a carbon tax or carbon pricing. It's not very favorable, right? Because especially in Switzerland, we don't even have sequestration, and transport cost to the North Sea is quite high, right? So, but with Power-to-X projects and CO2 storage project in form of energy, this could still be done, but we cannot do it at a larger scale, at the scale that we are looking at without the support from policymakers. So the CO2 pricing has to become favorable for this market to become really a place to people to invest and scale it up more.
It's a very interesting question. I think one thing looking at agriculture, margins are really, really small in agriculture. So the willingness there of an industry to invest in new technology and to consider sustainability is a challenge. So I think one thing is maybe we need to think from the policy level, what's the value we should be putting on food? Maybe we're going to have to pay a little bit more for our food, but I think the other thing is making use of these resources in terms of waste and others. So how these can also have added value as well.
Definitely, definitely. Both of you also talked about circularity, and it seems like there are a lot of many moving parts that need to come together. One question I had is, how can you actually make all the moving parts come together, and how do you coordinate all of this? Of course, Kumar, maybe on the Swiss scale, you're also moving from the campus model scale to maybe the VO scale. So how would that go about?
I mean, in the CO2 capture, this is something that we are trying to do already now with the capture, storage, sequestration, and utilization. So there is inbuilt circularity there. But if you talk of larger scale, I think, again, one has to work together with various partners, right? So we cannot alone do the capture and hope that somebody will essentially fully be successful in the utilization, and vice versa. One cannot just do utilization and hope CO2, pure CO2 will flow in somewhere in a continuous manner, right? So this all has to be worked together in partnership, and I think we have to see this as one joint effort and not as segregated competition. So this has to be very well done with each other. And I think this is why I'm so happy to, it's my pleasure to work on these kind of projects, because very difficult to find partners who are in different domains, and Solution for Sustainability project allows us to work with people who are working on very different topic that you don't typically work in your lab. So I think this will bring the circularity.
I think the circularity brings challenges both on the kind of the scientific research side, but also then on the infrastructure and kind of stakeholder side. I think on the scientific side, we have multiple biological systems working together in terms of growing and then bioreactors. So that is very challenging just to exploit this circularity when you have complex systems, and how to model these and how to co-optimize at a system level when you've got different timescales and uncertainties can be quite high. On the second side, then, to start deploying this, there's this, how do you get these different stakeholders working together and encourage people working in different domains with very different business models, very different goals, and that is definitely challenging to actually enable this circularity at a larger scale. And again, needs these projects and this bringing together of these different stakeholders and these different views and different challenges to move towards something more circular.
Thank you. Maybe one last question before we open it up to the public. That's more of a student question, but how can students contribute to your labs today? And more generally, beyond the technical skills, how can a student maybe get into sustainability startups? What would be your best advice?
Yeah, I mean, this is an excellent question. And I think the first step starts with the students interested and getting very involved and excited with, the coursework, and where they can get a strong fundamentals in math, science, engineering, right? Because that's the first part. And I think they should see this as a challenge, a rewarding challenge, because it's not just about passing the exam, it's about also really taking that part as sort of in a real-world experience that will happen from all these projects as they even go and join the industry. More likely than not, they will be working on sustainability-related topics. So that's how I think of the answer to the part number one. Answer to the part number two is getting involved in the lab through what is currently existing at EPFL, either through semester projects or through make projects, to sort of try and volunteer either for credits for the semester projects or not for credits through the make projects. And opportunities will open, I think, for students who are looking forward, who are dedicated. My own spin-off has actually a student who is leading the spin-off, a bachelor student from EPFL. So it's really about being open to ideas, and it's really about exploring and talking to professors, talking to different labs.
I think it's really interesting to see here the variety of different backgrounds everyone has, and all together we're working on this collective problems of sustainability, which I think really stresses the need. We need students from all these different backgrounds to come together and find creative solutions to these problems. So I think that's really interesting. This is a problem we have to solve, and we have to attack it from different disciplines and come up with creative solutions using our technologies in different ways. So I think it's the perfect opportunity, as challenging as this issue is and as dreadful as it is as well in terms of in terms of what we're doing to our planet and where we are. This is an opportunity, I think, for the next generation of scientists, of entrepreneurs, of technology developers to create creative solutions and to really reimagine the future.
Thank you. With these great words, we'll maybe take some questions from the public if you have some.
Yes, Tomoko.
So, well, thank you for this fascinating talk. So it's related to what Josie said, that there was, that the working together with different disciplines and so on. So Kumar, so you were leading this big collaboration, so covering a chemistry, physics, engineering, manufacturing. It's even more than disciplines, that the different sectors from academia to industry. So what do you think the key to make a success with those collaboration, and what we can learn from your experience of, because I see that it's still a challenge, this interdisciplinary or the collaboration for energy sector or on sustainability challenges that we really need to do, but see still barriers.
Excellent question, and I'm very glad to actually answer that question, because this is sort of related to, I'm quite passionate about this topic. I think as a scientist or professors or research labs, when we try to, often we try to solve the problem, and we're talking about applied problems here. So this is a given problem that we are trying to solve. And often this is not based on, it at least should not be based on, okay, I have this material or I have this chemistry. Let's see what application can I find, right? So it should be other way around. What is the challenge? What is the applied problem we are trying to solve, either related to the energy efficiency, the cost, the sustainability, life cycle assessment, and then how this product should be designed, right? So chemistry, material science, engineering, processes, right? So, and the way it should be done is, it should be the first process that should give a KPI of what should be the material performance, how should be the material be made, and so on, right? You can throw in a life cycle assessment there to make sure that the chemistry or the synthesis part is not so intensive. It doesn't depend on, like materials that are not there on Earth crust, or it's so expensive that it cannot be done. So I think this thinking process has to be sort of this way, in a sort of, you first design the process, you get the KPIs for what is going to be the performance, then you start looking into the material, if the material is there, whether the material is scalable or not. Then you can always find partners, right? So in this project, I was very lucky to find partners from STI, especially Vivek, who had this understanding of role to role. And then essentially, then you go and break the barriers from there on. So that was my answer to that.
And with that, I think we'll close this roundtable. Thank you very much to both of you.
Thank you.
Thank you. Thank you very much, Julian, for the moderation. We enter into the last session of this event. I don't want to make any mistake in the order of things. So I would like to ask Ianina Altshuler to come and present the third one. So the first two sessions were about solutions for sustainability. Went into something that goes a little bit beyond these projects, and it's from the roots of EPFL, from the day-to-day research that is happening. And we consider the earth ecosystems and land and soil. So Ianina, over to you. Yes, you may use this one.
Okay, thank you everyone for being here. So when Dimitrios contacted me and asked me to do a sustainability talk, I panicked because I don't think most of my research has anything to do with actual sustainability. So I had to zoom out a lot. So I wanted to talk about a little bit about ecosystem services. So ecosystem services are, in general, the services that ecosystems provide for us, basically for free. So these fall into these different kind of categories, and the example that's often given that's very tangible for people to understand is natural pollinators. So how much money would it cost us to pollinate all these trees that ecosystems provide us, basically this kind of service for free. So you can think about it in a sense of a forest. So we have a forest, And it can provide many kind of services for us. For example, it has supporting services, like it provides a habitat, has primary productivity that grows a lot of the trees, and it provides us with a lot of like nutrient cycling, for example. It has a lot of spiritual, recreational, and eco kind of services as well. So we group these into kind of like cultural services that ecosystems provide for us that are kind of have a monetary value but are not tangible. Some of the other services that ecosystems provide for us are provisional. So this is where we think about like timber, in terms of the forest, a lot of the wood that comes for our building materials, a lot of game meat, fish is associated with it, medicinal plants and mushrooms that could be harvested from forests, for example. And finally, one of the ecosystem services that forests provide for us are regulating. So these include like moderating climates, providing higher water quality, so a lot of filtration happens through these forest ecosystems, and also flood control. So you could see how all of these ecosystem services are provided kind of free of cost through these ecosystems such as forests. This is just an example. I mean, we have a ton of different ecosystems providing a variety of different services for us. And often we don't kind of think about the inherent cost of how much it would cost us to replace all these kind of services, and this is on the levels of like trillions of dollars. So I study mostly soil and soil microbial ecosystems. So I wanted to emphasize that soil plays a central role in many of these ecosystem services, providing like a very wide variety of things that we usually don't think about when we think about it as just dirt. So a lot of like nutrient cycling, a lot of like carbon storage is supported by soils, and then also in terms of the built environment, it provides a lot of foundation for human structures, a lot of our bioprospecting and kind of enzymes that are used for biological technologies and antibiotics are also prospected from soils as well. And a lot of this has to do with the microbiology that's found in these kind of soils. So I like to show this picture to my students and basically ask them the question of which of these two soils do they think is the quote-unquote healthy soil. So a lot of them get stuck on this like more rich, dark, kind of like tasty-looking soil versus like the very dry, crusty one. And then I usually show them this photo of the forest and say, how about now? Do they have like a difference of opinion in terms of which of these soils is considered quote-unquote healthy? And then I complicate it a bit more and say, how about this soil, which is, it could produce a lot of crops and stuff, but maybe it has really high contamination of, heavy metals or whatnot. And maybe this soil, in turn, doesn't look very great, but it has a lot of carbon storage and water filtration capabilities that is very key for, surrounding environments that are, around the forest, the human ones. And then this soil that looks almost maybe completely useless, in fact, has really high capability for microbial biotechnological applications. So a lot of extreme enzymes and extreme microorganisms that we can harvest from this kind of quite dry, hot soil have tremendous uses for biotechnological approaches. So basically what we consider a healthy soil depends on the context and who's asking the question. So if you're asking the question in terms of agriculture, a healthy soil might be one that's, full of nutrients and can produce basically a huge amount of crops. When we're talking about the built environments, maybe you want stability, when you want predicted amount of water resources around, maybe you want to plant certain kind of trees that are aesthetically pleasing to people. You might have a different idea of what a healthy soil is in that kind of system. In terms of climate, maybe you consider a healthy soil one that can have a really high storage of carbon in the soil and maybe doesn't produce a lot of carbon dioxide. So these are mangrove trees They're in around coastal ecosystems, and they have a really large effect on preventing flooding into the surrounding areas. And also they have really, really high carbon storage capability. So a lot of the carbon there is degrading extremely slowly, so they are counted as like carbon sink ecosystems. And in terms of like an ecological perspective, you might see, you know, an ecologist looks at soil and they consider soil to be healthy if it has like a very high biodiversity of organisms that are living in that kind of soil. So whether soil might be, you know, healthy for agriculture, it might not be healthy for climate if that soil is emitting a lot of carbon in the process of growing this kind of food. So I wanted to then pivot to my study system, so not so tasty soil. So I work in the Swiss Alps, in these kind of very dry and cold soils. And a lot of the things we do is my students are basically kind of digging around in soils and the dirt and trying to figure out, is this soil basically healthy if we really zoom out to the kind of questions I'm asking. A lot of the stuff that we also do is we do trying to predict how the soils would react to in a warming climate. So if we have changes in precipitation and we have different amounts of moisture that is deposited into this environment and we have higher temperatures, what will be the end result of this soil? Is this soil going to be more healthy, let's say, or less healthy? Is it going to be more biodiverse, less biodiverse? Is it going to act as a carbon sink or as a carbon source? So we have these warming experiments that we set up across the Alps. Hopefully some of you hike, so maybe sometimes you will come across one of these and, you know, don't knock it down. The hikers in Switzerland are extremely respected. And we haven't lost a single one of these warming chambers that we have set up. So on kind of like a larger scale, it looks like this. This is in plain mort. So despite what the name suggests, it's not actually mort. It's quite living in terms of the soil. So the soil is living, respiring, and it's quite alive. I got this picture. I didn't take this picture. My students took this picture after the fact, and I was extremely concerned because it's extremely dangerous to bring a car there. So after this, I told them no more bringing the car up there. You're gonna actually have to hike up with all the equipment, but that's okay because everything is now set up. But we have these kind of normal, like current plots that we keep monitoring, and these warming plots that we set up to kind of see how climate change is going to impact our particular soils. And we have this, the plan for this is having like a very long-term monitoring of these kind of soils to see how they will evolve with warming temperatures. So I wanted to kind of really briefly summarize what we see so far. So the first thing that we noticed really quickly that these soils are basically islands of biodiversity. So each of these peaks that we go to, and we go to quite a few of these peaks, they are quite diverse. We thought that originally they'll have a lot of like redundancy between them and they'll have really high overlap. But I think because of the way the Alps were formed, they have very different bedrocks and very different chemistry across these different places. So we see very different islands of biodiversity across the different peaks. We also see that these soils are alive, they're respiring, they're producing carbon dioxide. I mean, this is a natural process for all soils, including ours as well. But what's interesting is that we see actually methane, also like a greenhouse gas of concern, is actually being taken up by these soils. So these soils are actively working as methane sinks. So you can think about their ecosystem service for us is actually taking up methane from the atmosphere and sequestering it into the soil itself. Then we look at the impact of warming as well, and we see that we're losing the biodiversity across the different peaks with the increase of the warming, so that's concerning for us. So we're losing one of our ecosystem services as a source of these like maybe potentially novel enzymes downstream. So for this, we started kind of like biobanking the current microbial organisms that we find in these. We see an increase in carbon dioxide emissions with these warmer soils in these overall cold soils, which is very unfortunate. But in in parallel to these increase of carbon dioxide, we don't actually see an increase in uptake of methane with warmer temperatures, which is unfortunate. So the next steps of our lab's research is to take these microorganisms that we have found that can take up methane. So these are methanotrophs. So they eat methane for breakfast, lunch, and dinner. And we're starting to develop parameters how we can take these organisms, input them into the soil, and then now we're starting to see that with these kind of, let's say, engineered soils, that they are starting to take up more methane compared to the natural soils. Okay, thank you so much.
With that, I would like to invite Professor Rizlan Bernier-Latmani, who will focus actually a little bit on soil decontamination. So.
Okay, so good afternoon. So as Dimitri said, I'm going to jump off of what Ianina presented, which is soil health. How do you define soil health, and talk about a specific problem with soils, that translates, unfortunately, into agriculture, which is arsenic in rice. So you all know arsenic. It's a toxin. It's naturally occurring. It's present everywhere in soil across the world at low levels. And unfortunately, it's for people exposed to arsenic, and I'll explain how the exposure takes place later. Chronic exposure to arsenic can lead to severe health effects. For example, the first symptoms are the skin lesions that are depicted here, keratosis, melanosis, and later leading to lung and bladder cancer that have the highest mortality. And also for the younger population, either in utero or the young folks, there's an impact on cognitive development and on birth weight. So altogether, not a great element to be exposed to. And fortunately, it turns out that rice, the rice plant, is a natural hyperaccumulator for arsenic. In other words, if you look at the concentration of arsenic in soil, and then you measure the concentration in the rice grain, there's actually a concentration effect. And this is due to the physiology of the rice plant. So I have this graph here, which is often of interest to people, which looks at the concentration of arsenic in rice across different varieties. And you can plot this. I plotted it by variety, like basmati, jasmine, etc. You can also plot it by geographical origin of the rice and also rice processing. So if you see on the top there, you have polished white rice. So the rice, as you know, rice comes with a husk. You need to remove that. It gets brown rice, and you remove the bran, and then you get white rice. So white rice is first on the left, and then brown rice on the right. And brown rice in general contains much more arsenic because the bran part of the rice contains a lot of arsenic. In any case, the point I'm trying to make here is that depending on the rice variety, you're going to have different concentrations of arsenic. And the Swiss and EU threshold, which is 150 ppb, is commonly exceeded. These are data from the Food and Drug Administration in the US, where they just basically took rice off of supermarket shelves and measured the arsenic. And then for the brown rice, there's a different level, which is a different limit, which is 250 ppb, which is also commonly exceeded. So this is a problem because, of course, food through rice is one way of exposure, one way that people are exposed to arsenic. So now I just want to tell you a little bit of background about arsenic chemistry and how microbes transform this chemistry, because it will help us explain how we can mitigate some of these issues. So arsenic looks like this. You have inorganic arsenic, and this is what's present in soils usually. But microorganisms can methylate this arsenic by putting in a methyl group, as you see in red there, either 1 or 2 methyl groups. And then this dimethylated arsenic can be transformed into a volatile form of arsenic, so a gas phase. It can be further methylated, which is forming a trimethylated arsenic, which is also volatile. So essentially, we have 2 forms of volatile arsenic that are produced via microbial transformation of the inorganic arsenic that's present in the soil. So if you look at this sort of diagrammatically, we see that in the soil, these microorganisms here represented by this green blob can transform inorganic arsenic into ultimately volatile arsenic. And then this would allow the removal, the net removal of arsenic from the soil into the atmosphere. And so the other thing that's important to know, I'm sure you all know this, that rice is grown in flooded, and most rice is grown in flooded environments. And how do you flood these rice paddies? Typically, it's with groundwater. So collecting groundwater and pumping it and bringing it and saturating the rice paddy. However, in many of these regions that grow rice, so in South Asia and Southeast Asia, there is arsenic that's present in the groundwater. So essentially what's happening, and this is just a map to show the probability of having more than 10 ppb, micrograms per liter arsenic in groundwater, and the regions that are darker means that there's more probability, and 10 micrograms per liter is the drinking water limit. So in essence, by pumping groundwater, using it to irrigate rice, farmers are actually increasing the load of arsenic into their rice paddies, exacerbating this problem. So the strategy, the idea here is to engineer biological arsenic volatilization by stimulating this microbial arsenic methylation. And this can be done in 3 ways. First, by bioaugmentation, meaning by adding microorganisms that very effectively methylate arsenic and volatilize it. Option 2 is by biostimulation, meaning that you add and make an amendment, a chemical compound that stimulates the existing microbial methylators. Or third, you manage the land in some way that stimulates arsenic methylation without adding anything. And so if we were able to do this, then we would envision the volatilization of methylated arsenic, which can be done at large scale. And if one wants to, they can also trap this gas that's produced through microbial methylation. Now, what's standing in the way of doing this? Well, we need to know how we can promote arsenic methylation. And so we know a little bit. And so what I'm going to tell you now for the rest of my talk is what do we know? We know that the absence of oxygen enhances microbial methylation. So this I'm showing a study from 2024 from somebody not in my lab, showing a plot. This is a plot, a paddy field with the grid. And they measured the soil EH, which is a redox potential. So the more negative, the more reductive, the less oxygen. So we see that we have a hot spot of low EH here, and that corresponds to a hot spot of methylated arsenic. And so this is one of the evidences. There's many other studies, just to show you an example. We know that if there's no oxygen, so the flooded soil, it promotes arsenic methylation. Therefore, one strategy could be to, in between cropping cycles, keep the soil flooded in order to continue to conserve the low redox potential that allows this promotion of volatilization. The second thing that we know is that nutrient limitation promotes arsenic methylation. So this is a study from my lab where we looked at if you provide less organic carbon, so you can read this graph here as how much methylation is happening over time. This is low carbon and this is high carbon. And so we see very clearly that at the low carbon case, we have much more arsenic, methylated arsenic, than the low carbon case. And so actually by limiting nutrients, so low organic carbon, we promote microbial arsenic methylation. So practically speaking, this would mean that between cropping cycles, but to remove the rice straw, which is usually left in the field, and allow this, the soil to be bare, flooded but bare. I can tell you, if somebody's curious why actually nutrient limitation promotes methylation, I'm happy to talk about it. but there's no time now. So those are the two things that we know for sure. The third thing is that some research has shown that the amendment of sulfate in the form of gypsum, calcium sulfate, promotes arsenic methylation in the absence of oxygen, but we don't know why. So the underlying mechanism is unknown, and so this is something that is worth looking into. And finally, what we're trying to do is to have high throughput isolation of arsenic methylating organisms to identify which ones are very effective or have the highest yield of methylated arsenic to use that are isolated from soil, so the naturally occurring organisms, to use as an amendment to soil. Like you add fertilizer, you can just add arsenic methylating bacteria. Okay, so with this, I'd like to acknowledge the funding and, of course, you for your attention.
So thank you very much. I would like to invite also Fatima. Thank you for joining. As you may, you don't know, Fatima Azahra El Zain, she is a master's student, and she has agreed to moderate this discussion. Thank you very much, and it's over to you.
Thank you. I would like to thank you for both your presentations. They were really insightful. Unfortunately, we had a third participant to this roundtable that is not here, but I would like to share with you some insight that he brought to me about this topic, and I would like to know your opinion about it. So he said that a not contaminated soil is actually a soil that is not analyzed enough, and that the question is always about how, to define how much contamination you would tolerate according to how you're using the soil. What's your take on this?
Okay, so just to be clear, the point is that you can hear me? Okay. The question, just to be clear, the question is, uncontaminated soils are not often investigated. Is that what you're saying? So determining the sort of the level of health based on biodiversity is not pursued sufficiently.
Yes, the point of that statement was more like we have this idealization of a soil that is perfectly healthy with no contaminants, but that's actually biasing our the soil that is provided, like in urban contexts, because we are having this ideal, but actually, whenever you're going to analyze thoroughly a soil, you're going to find contaminants. That was more like the.
Okay. Well, it's hard to, I mean, it depends where you look. In an urban environment, yes, it's likely that the soil will be contaminated either by organics or metals. This I would agree with. But I mean, more generally, I think that's not necessarily true, right? I mean, there are soils that are pristine, less and less, but there are soils that are not, I would consider not contaminated. I mean, you can just use the law, right? There is very clear thresholds indicating what is contaminated and what is not. So this is something that's relatively easy to differentiate between the two types of soils.
Thank you. I just showed you how the industry and the research field usually conflict in statements. Thank you for showing how a challenge it is to reconcile kind of both. Now let's go back to your researches. So. What are the key factors that you identify and that allow you to choose a soil remediation technique rather than another?
Hello. It's based on. I wish I had an elegant answer, but it's really based on practicality and like what we've been trained in, like what my basic science background is in, right? So I tend to gravitate towards trying to engineer the soil maybe by adding different kind of microbial agents to it, right? Somebody else might try to engineer it by adding certain nutrients to it. So I think I wish I could say it's like an ecological perspective. We do a risk assessment of which, intervention strategy is better, but usually it's more practical based on like what you're good at. Sorry.
I mean, well, my answer might be slightly different. So I think you have to take into account the characteristics of the soil. I mean, I'm looking beyond biology. There's also physicochemical strategies for soil remediation. And there, the limiting factors are often the type of contaminant and often mixtures of contaminant, the physicochemical characteristics of the soil, and then what the environment is. I mean, we have situations where the soil is beneath a building. Okay, you have to remediate, and it's serving as a source, as a point source for groundwater contamination. What do? If the building is protected, which I have cases like this, the building's protected, you can't dig underneath. How do you remediate this soil? And that, the context is going to be determine what you can do and what you can't do, which is most of things you can't do, but there are few options that you can use.
Can I follow up? Yeah, of course. Not exactly on the building, but this is also why it's important to have multiple people working on a problem at the same time so they can bring in their own perspectives. I was working at one point in the Arctic when we had an oil spill, right? And then, my approach to bioremediating that place will absolutely not work because it's really too cold. And the more practical one was just burning the oil, which doesn't sound very beautiful, but like that was the most practical, thing that we can do for the community that's living there.
Okay, thank you. So a lot about the technical and the scientific capabilities and constraints, but also thinking about the environment, the surrounding, and the people. So the effects of this intervention. And on that, how do you mitigate these effects? So you're coming with an intervention in soil remediation and could have like underlying effects on the soil, but also on its use. How do you take this into consideration in your research, and how do you mitigate for that?
Yeah, so I mean, the most important thing to consider is the endpoint. So if you're remediating in a soil, you have to get it to a certain point that it meets the requirements, the legal requirements of a remediated soil. The second thing to consider is if it's in an urban environment, for example, you have people living around it, and so what kinds of emissions will occur and take place, and how can you prevent those from harming the people around? So it's hard to, I mean, there's really a large number of considerations to take into account, and it is why I think what Ianina was saying is that you'd work on a team with different people, with different expertises, and then build this remediation strategy based on that. And then in terms of the impact on downstream, like beyond health, like there's a big issue with contamination of groundwater. So the first thing you do if you have a soil that's contaminated, you know that you have a contaminant that is highly mobile, is you put a barrier to prevent this contaminant from flowing down gradient into the groundwater or into surface water.
That's a perfect answer. No, but community buy-in is really, it's one of the things we never think about, but it ends up sometimes being one of the biggest hurdles.
Maybe my last question before we go to the audience. We're mentioning a lot of regulation, and here in Switzerland we have a lot of regulations in terms of soil quality and soil health. So it's helping because it's a guideline for you to assess the contamination and your goals after the remediation. But do you think there are any improvements that could be made in terms of regulations or others for you to be able to scale up your projects or make the microbe-based approach more appealing, I would say, to soil remediation techniques?
I almost feel like it's not even regulation, but changing regulations, but it's like ensuring their compliance is like across like the industries is like almost a bigger hurdle.
What I've encountered is that the industry, the environmental, usually environmental consultancies that deal with contaminated sites, one of the biggest hurdles that I've found is that it's a conservative industry. They're used to doing things a certain way, and it's difficult to, adopt new technologies, new ideas. For bioremediation is something that's been around for 30 years, but there are very few bioremediation projects in Switzerland, whereas in Europe, in North America, this is something that's relatively, I wouldn't say common, but can be happen on a regular basis. But here, there is a certain, so it's not so much the regulation as much as the culture of the consulting world. And I think, and I hope that this changes, and I teach all my students to be aware that there are many different technologies. There's not just the usual technologies that are being used, which is, to be honest, mostly basically excavation. This is how most of the sites are treated in Switzerland right now. So I try to teach the next generations to think about new technologies, more environmentally friendly technologies that hopefully will take hold.
Thank you, great. Any questions from the audience? Yeah.
Hi, thanks so much for your talks. This was super fascinating. So I do the ethics of artificial intelligence from a sustainability perspective. I'm looking at the environmental justice issues of making and using and disposing of AI, so the mining of precious minerals, the electronic waste. So I have questions for both of you. In terms of arsenic, and arsenic being present in the soil, then of course this limits your capacity for clean drinking water and agriculture. And you were talking about just strictly rice, but are you studying, or do you know of anyone studying, the link between data centers and the impact on the soil and the presence of arsenic in the surrounding area from data centers? And then my question for Professor Altshuler is similar. Do you do research, or do you know anyone doing research on the impact of data centers and the soil quality surrounding the data centers? And I say this too because I think it was the first panel, they were talking about how there's approximately 80 data centers in Switzerland, and I got the impression that there's no cap, yeah? That it's sort of, we're gonna go, right? And so is anyone studying the soil quality in relation to this infrastructure of artificial intelligence popping up, especially here in Switzerland?
I don't have a great answer for you, but when they were presenting that, I turned to Rizlan and I said, you should sample the soil there.
Yes, you should. Please do it.
Yeah, but for me personally, in my research, I have not thought about that aspect at all, but maybe it's more relevant to your research, actually.
Yeah, I mean, I don't know of anybody looking at that, to be fair. I think most people, when they think about data centers, AI, etc., and the impact on the environment, they think about two things. One is the mineral resources, so the mining of metals, etc. So this has a negative, typically a negative environmental impact. And two, the water. So the cooling of these data centers requires water. And this is, in some places, water is a limiting resource, and even in Switzerland, it's not yet, but it will become, unfortunately. So this is something that those are the typical topics that are focused on it. I don't work on either of them at the moment, but this is definitely growing. This is an area that's growing.
Thank you. It seems we have more or less uncovered a new area of research, so maybe. You never know. Okay, thank you very much. Is there any other question? I think, if not, I would just like to thank once more the panelists and the moderator. Thank you very much, Fatima, for preparing this session. And well, with this conference, Science for Sustainability, ends. I would like to thank all the participants, be it speakers, moderators, or and of course those in the audience. We will continue with a different event, so we just have about 20 minutes to prepare the next one. So again, thank you everyone, and well, all the best, all of you. Thank you.